Atoms are relatively simple particles. While they are the smallest unit that can retain the property of a sample, they can be divided into smaller subatomic particles that don't retain the properties of that sample. You'll be responsible for quickly determining how many subatomic particles are going to be present in a neutral atom of an element or an ion of that element, which we'll talk about later. I'll elaborate on how we do this when we get to section 1.2 because we're going to use the periodic table to help us with this. For now, focus on learning what the particles are, where those particles are located in the atom, what the charges on those particles are and what that means for the charge distribution of your atom, and what the mass of those particles are and what that means for the mass distribution of your atom. Now again, let's start with some definitions. Here's your atom, or the smallest indivisible particle that retains the property of the element. Or this is what atoms look like when we see them in the textbooks, like a ball. A tiny little spherical package on its way to building all matter and life as we know it. Now the atom is spherical, so our model works well there. But this model definitely makes it appear as though there's a definite edge and end to your atom, which really isn't true. So the model works less well there, and we'll see why in a minute. Particles. Now we're only going to worry about 3 bigger subatomic particles and not the fundamental particles like the quarks, bosons, and leptons. The first of those particles are the protons. Protons have a mass of 1 atomic mass unit, or AMU. Protons are positively charged. The second particle is going to be the neutron, which also has a mass of 1 AMU, and they do not carry a charge, or in other words, they are neutral. Your third particle is the electron, which has almost no mass. So little that we go ahead and round that down and we say 0 AMU. Electrons carry a negative charge. Some notes. First, let's let the significant figure please take a deep breath. The masses associated with the subatomic particles are not brilliantly rounded whole numbers like these shown here. There are a lot of decimal places associated with their mass values. The AMU is a very small unit of measure. Compare 1 AMU to the mass in grams, which is a really very small unit of measure itself. Rounding to an easy to handle whole number here isn't going to change the overall mass of the atom enough that our answers are way off the mark. So we do that. Do not, under any circumstances, work to memorize these more precise values given in the table. They are simply here for illustration purposes. Next, the colors here are completely arbitrary. Your subatomic particles don't have colors associated with them. I just chose colors I thought contrasted, so you might be able to see the difference when I elaborate on atomic structure here in a minute. And lastly, the size of the electron is smaller than the size of the other 2 particles. The electron is so very super small, so I was working to indicate that fact. This difference here is no way to scale though. You wouldn't be able to see the dot for the electron if I had drawn it to scale. You'll need to know the mass and the charges of all of these particles. But since subatomic particles are really only important to us when they come together in combination to form atoms, we have to move beyond just a table of facts and talk about atomic structure. The nucleus and the electron cloud. Now here my colors are very much on purpose. The nucleus of the atom is going to be positively charged. The color here matches the color of those positively charged protons we saw earlier. Your electron cloud will be negatively charged, and the color of the cloud matches the color of the negatively charged electrons we saw earlier. Before I move one step further, notice how much smaller the nucleus is than that electron cloud. Now again, I can't really do the ratio correctly because you wouldn't be able to see the nucleus if I made it the right tiny size. It's really that much smaller than the electron cloud. In fact, it contributes only 1/10 trillionth of an atom's volume. This means that most of your atom's volume is attributed to the negatively charged electron cloud. Notice also that I made the cloud larger than the atom itself. This isn't because I'm bad at PowerPoint. It's because there's a chance of finding an electron an infinite distance from the nucleus. That probability is pretty low, but it's not 0. So the size of the electron cloud is not limited to the atomic radius of the atom itself. Cloud using an actual element. We're going to keep it relatively simple and look at helium. Here is helium's entry from the periodic table. You'll see the periodic table in the next section. For now, know that the whole number at the very top of this entry tells me how many protons are going to be in my atom. So helium has 2 protons in its nucleus. Let's say that we're talking about the most common helium atoms, which also have 2 neutrons. We've just built the nucleus of the helium atom. The nucleus houses both the protons and the neutrons of an atom. It's going to be found in the very center of said atom. The rest of your atom is that electron cloud. Because we're dealing with an atom of helium, I know that it's going to have 2 electrons associated with it. Know that your electrons move very quickly and very freely through the entire electron cloud. Your nucleus, and therefore your protons and neutrons, are fixed in one spot in your atom. The electrons definitely are not, but I have to put them somewhere. And now you know where the subatomic particles are located in an atom. The nucleus has the protons and the neutrons, and the electron cloud has the electrons. Get better. Remember that each of these particles have a charge associated with them, shown here. Your protons carry a 1+ charge, and your neutrons do not carry a charge. This means that the nucleus is a positively charged center in your atom. Positive charge does not reside anywhere else in your atom outside of this nucleus. Since our helium atom has 2 protons, the charge in the nucleus is equal to 2+. If our atom had 38 protons, the charge on that nucleus would be 38+, 1 positive charge for each proton present. Now, some of you are thinking, if the nucleus is really that small, and if there's nothing but positive charge in the nucleus, how does it stay together? Why aren't the protons repelling each other? Well, there's definitely electromagnetic repulsion between the protons. Things of like charge will repel each other, after all. But there's a relatively complicated idea called the strong nuclear force that's stronger than this repulsion. That strong nuclear force, which binds the protons and neutrons, holds our nucleus and thus the whole atom together. Since the neutrons are neutral, they add to this strong nuclear force and they help the nucleus remain a small, very densely packed group of particles right in the center of your atom. Since electrons are negatively charged and they reside in the electron cloud, that electron cloud also has to be negatively charged. Notice here that I've placed my electrons as far apart from each other as possible. Unlike the nucleus, there's no strong force to overcome repulsion in the cloud. Your electrons will work to move as far apart from each other in 3-dimensional space as possible. This fact leads to the shape of our molecules, which we see in Module 7. It also leads to a mostly empty electron cloud. The majority of your atoms just dead space, which gives the electrons room to situate themselves. Your nucleus is positively charged. Your electrons are negatively charged. There's an attraction between the nucleus and the electrons that keep the electrons from just leaving the cloud and going elsewhere. Now, in our first image, I just threw the fact that an atom of helium will have 2 electrons. All of your atoms have to be neutral overall, or they will have an equal number of positive and negative charges. Since the periodic table told me that helium had to have 2 protons, each of which carry a 1+ charge, then I know that I also have to have 2 electrons present. I'll need the same number of negative charges as I have positive charges in order for those charges to cancel and my atom to be neutral. This is not going to be the case for ions, but every atom will have the same number of protons as it does electrons. Now you know where the subatomic particles go and what that means for the charge distribution of the atom. The mass associated with an atom. Now, similar song, different verse. Instead of the charge on the particles, I've indicated the mass of the particles. Electrons have almost no mass associated with them. Since nothing but electrons are found in the electron cloud, we say that the electron cloud has no appreciable mass associated with it. This means that the area that represents the overwhelming majority of my atom does little for me mass-wise. Almost all of the mass of an atom, 99.97% of it's going to be found in the nucleus. Each proton and neutron found in the nucleus has a mass of 1 atomic mass unit, which is already short, but the chemist sometimes shortens AMU to U. With our helium atom here, there are 4 total particles that have a mass of 1 AMU. So our nucleus will have a mass of 4 AMU. The mass of a nucleus, and therefore the atom, is equal to the sum of the number of protons and the number of neutrons. Now you know where the subatomic particles go and what that means for the mass distribution of your atom. All right, now you know an atom can be divided into 2 main areas, the nucleus and the electron cloud. The nucleus houses the protons and the neutrons as a densely packed core inside the center of your atom. Since protons have a charge of 1+ and neutrons are neutral, this means that the nucleus carries a positive charge equal to the number of protons. Since both of these particles have a mass of 1 atomic mass unit, the nucleus will have a mass equal to the sum of both of these particles. The electron cloud houses the electrons. Unlike the nucleus, the electron cloud is the opposite of dense and instead is mostly empty space. There's no appreciable mass in the electron cloud, which is negatively charged because it houses only electrons. You'll need to take all of the info from all of the slides and reorganize it so that it makes the most sense to you so that you can use it as a study tool.